In this video, we're going to talk about the reduction and oxidation reactions of monosaccharides. Recall that monosaccharides are organic compounds, organic molecules that contain many hydroxyl groups, and they also contain either an aldehyde or a ketone functional group. So because they contain these aldehydes and ketone functional groups, they will be able to undergo reduction and oxidation reactions. In the last part of this video, we're going to look at how these oxidation reactions have been exploited in technologies that allow us to monitor glucose levels either in urine or in blood. So let's recall what a reduction of an aldehyde is. We looked at this when we talked about organic chemistry reactions. And here, how this reaction worked is we would start with an aldehyde, and then in the presence of hydrogen and a palladium catalyst, this double bond between the carbon and the oxygen would break, and a hydrogen would be added across that double bond. So we would add a hydrogen to the carbon and a hydrogen to the oxygen, and this would produce a primary alcohol. Let's see how this will work in the context of a carbohydrate. So recall that your carbohydrate does interconvert between the cyclic form and the open chain form. When it is in the open chain form, that's when it's going to have this aldehyde group that is available for reduction. While it is in the cyclic form, that aldehyde group is not present. So it has to first interconvert into this open chain, and then this is the species that will be reduced. So now when you have this open chain or acyclic form, if you add H2 and palladium catalyst, then this double bond will break and you will add the hydrogen across that double bond. And you essentially go from having an aldose, meaning a carbohydrate that has an aldehyde, to an alditol, which is an alcohol species that was made from an aldose, which is why it gets the name alditol. Recall that the ending OL is referring to an alcohol. And here we have made a primary alcohol. So we use the term aldose to describe the carbohydrate when it contains its aldehyde, and we use the term alditol when we have an alcohol that was derived from an aldose. Now let's look at their oxidation reactions. So let's recall that for oxidation, we would have an aldehyde, and then this hydrogen here would pick up an oxygen. Because recall that an oxidation reaction is the increase of carbon-oxygen bonds or the decrease of carbon-hydrogen bonds. So in the presence of an oxidizing agent, if you have an aldehyde and you have this hydrogen here available, which is characteristic of an aldehyde, then we can create carbon-oxygen bonds by adding an oxygen here. That is how we make the carboxylic acid. So let's look in the context of a carbohydrate how this would work. So here I have glucose, which is an aldose. It has that aldehyde group up here. And then in the presence of an oxidizing agent, in the context of carbohydrates, that oxidizing agent is often a Benedict's reagent. So anytime you see Benedict's reagent, immediately you know that that is an oxidizing agent, and it's shown by these copper species here. Okay, so we have glucose, we have an aldehyde group, and we have an oxidizing agent. So what this means is that that aldehyde group can be converted into a carboxylic acid, where we can increase the number of carbon-oxygen bonds. And that is why we go from having glucose, which is an aldose, to gluconic acid, because species that have a carboxylic acid derived from a carbohydrate, we call those aldonic acids. And that is now because it contains a carboxylic group up here. All right, so what about ketoses? So we talked about aldoses, they can be oxidized. What about ketoses? Well, ketoses, like we learned previously, whenever you have a ketone functional groups are unable to be oxidized. And that is because the carbonyl carbon does not contain a hydrogen where you can now add an oxygen in there to create carbon-oxygen bonds or reduce carbon-hydrogen bonds. There's no carbon-hydrogen bond here, so this is unable to be oxidized. This is still true for the ketone form of a carbohydrate. So here I'm showing fructose, where it has a carbonyl group in the second carbon, making it a ketone. But what does happen with carbohydrates is that this can actually rearrange. This fructose can rearrange to form an aldehyde, where the groups in carbon 1 and carbon 2 basically swap. You can think of it as them swapping. And so now you're going to have your OH group in carbon 2, and the carbon double bonded to the oxygen is now in carbon 1. And this is going to create an aldehyde. So when this rearrangement happens from fructose to now having an aldose, meaning you now have an aldehyde group. Now, in the presence of Benedict's reagent or an oxidizing agent, in the presence of that, then now this species, the one with the aldehyde, can be converted to a carboxylic acid. So while ketosis, this species, when it has the ketone, while those are not able to be readily oxidized, when it rearranges, this species can then be oxidized. And this is how we can go from a ketose, or a species that has a ketone, to a species that has a carboxylic acid, is because there's this rearrangement as an intermediate. We will be looking at oxidation and reduction of carbonyl groups extensively when we talk about the metabolism of carbohydrates. These are actually going to be really common reactions in metabolism. Okay, let's apply what we just learned. We're going to draw the organic products formed when each monosaccharide is treated with the following reagents. In the first one, we are going to do H2 and PD. So if I have hydrogen and I have palladium catalyst, this means I'm doing a reduction reaction. So I will write H2. Okay, so if I am reducing my aldose, so I know this is an aldose, I have an aldehyde group up top. That means I am going to add hydrogens across this double bond, carbon-oxygen double bond. So I'm going to go ahead and break that carbon-oxygen double bond, leaving just one bond there. I'm going to write in that hydrogen here. And now I'm going to add the two hydrogens that come from my H2. One is going to go on the carbon, the other one is going to go on the oxygen. And then I can continue to write in the rest of my molecule. So I'm going to number the carbons just to keep track of all of my carbons. And then the OH groups do need to go on the left-hand side. Make sure you do not change the stereochemistry of your product. So with that, I'm going to go ahead and redo or condense this group up here, because if you look, you see this is just a CH2OH group. So I'm going to rewrite it similar to how it's written down here, just to make it a bit more condensed. So this alcohol that we have made, CH2OH, this is what we refer to as an alditol. It came from an aldose, and now I have a primary alcohol. All right, let's look at the second reaction. So now we're going to do copper 2+ and OH-. And immediately I recognize these are reagents that are used for oxidizing reactions. So I see, since I have an aldose, I have an aldehyde group that can be oxidized. So this aldehyde group located in carbon 1, that is going to turn into a carboxylic acid. So I'm going to go ahead and write that in. And then I'm going to write in the rest of my carbons. And that is it. We have now made an aldonic acid. So this, we call this an aldonic acid. All right, let's do a slightly different problem. It's the same idea, but now we're going to have a ketose sugar. All right, so what product is formed when each compound is treated with Benedict's reagent? The first thing to recognize here is that this is just an oxidizing agent. So that means that if we have an aldehyde, we can turn that aldehyde into a carboxylic acid. So in the first example here, I do see that I have an aldehyde. So all that means is this aldehyde will be converted to a carboxylic acid. And then the rest, so I have 1, 2, 3, 4, and 5. I'm going to go ahead and draw a Fisher projection just to make it faster. And then this means that carbon 2, carbon 3, and carbon 4 are chiral centers, and that's why they get those crosses. We covered how to draw Fisher projections in a previous video. And that's it. And this is the carboxylic acid that you get, which again is a type of aldonic acid. All right, let's look at the next one. The next one, I realize that I have a ketose. So this here is going to be a ketose. And while yes, ketones cannot be readily oxidized, we do know that in the context of carbohydrates, these monosaccharides can actually interconvert, where these two will rearrange with each other. So the carbonyl group will go up to the first carbon, and the OH group is going to go down to carbon number 2. So that means I now have an aldehyde in carbon number 1. It's carbon 1, 2, 3, 4, and 5. Then in carbon number 2, I'm going to have this OH group. That means I have an H on the other side, so that's carbon 2, 3, 4, and 5, which bears the CH2OH group. And then that means the other carbons will maintain their OH groups. All right, so now since my ketose has rearranged into an aldose, meaning I now have an aldehyde group, this can now undergo oxidation. So in this step, I just rearranged my molecule. Now this carboxylic acid, this aldehyde group can be converted to a carboxylic acid. And I'm going to go ahead and draw this as a Fischer projection so that it's faster. So it's just carbon 2, 3, and 4. And all of the OH groups will appear on the right-hand side. Okay? And that is how you can get, this should be a carboxylic acid. And that is how you get an aldonic acid from a ketose. Okay, so why are these reactions important? Well, we've actually been able to use these oxidation reactions in order to develop technologies, specifically technologies that can measure the glucose levels, and often we will see it does so indirectly, but that is a way that we can measure it. So let's look at glucose test strips. So how do we use the oxidation reaction here? Well, you're going to see that one of the reagents here is a glucose oxidase. We're going to learn that names that end in ASE are actually enzymes. So glucose oxidase is an enzyme that's found in fungi and insects. And how it works is that it will take an aldose, and in the presence of oxygen, which is why oxygen is the other reagent here, in the presence of oxygen, it will actually carry out an oxidation reaction. So we can go from having glucose to having gluconic acid, because now I've converted my aldehyde to a carboxylic acid. But in this reaction, we also produce this group here, which is hydrogen peroxide. And in glucose strips, this hydrogen peroxide further reacts with reactants that are on the strip to produce a colored product. And this is what we measure when we use these test strips. Because what this means is that if glucose is not present, if there is no glucose present in urine, then that means this reaction is not going to take place. And therefore, you will not get a colored product. But if you do have glucose, then this reaction will happen. You will produce H2O2, which will then further react to produce this color. And that is how you can know whether you have glucose present or not. That is in test strips. Let's see how we would use this oxidation reaction in digital glucose meters. So here, again, we are interested in measuring the amount of glucose that we have present in the blood. And in this case, we're also going to have an oxidizing agent to convert it to carboxylic acid. But what we are measuring here is actually the amount of oxidizing reagent that reacts. So it's also an indirect measure of glucose. Realize how in the test strips, we didn't measure glucose directly. We're actually measuring a product that should appear if glucose were present. A similar idea is happening here in the digital glucose meter, where we're not measuring glucose directly. What we are measuring directly is the amount of oxidizing agent. So that if we don't have any glucose present, then we have all of our oxidizing agent there. But the more glucose that we have here, the more oxidizing agent is going to be used up, and that is what the digital meter ends up reading. And so this is how we can use our knowledge of oxidation reactions to develop technologies that can be very useful in health and medicine.